Okay, so in this example, what we're going to do is we're going to connect the concept that we just learned about local linearity. And local linearity says that if you zoom in far enough into any curved function, that it appears to be linear. And this is good for us, because if we zoom in right now, you see this is good for us because the red line here and the tangent line appear to be the same when you're really close to the point of tangency. So what we're going to do is we're going to do this example together. This example says, without a calculator, use linear approximations to determine the square root of 3.91. So as we explained earlier, the linearization formula is this. Now Lx is what they use, and that's going to be the estimated value. So 3.91 we're going to say is right about here, okay? Right about here. So this right here, 2, is f of x. 4 is x, right? We have x and f of x. That's known. That's the known value. So from there, we are going to try to estimate, and this is drastically over, it's not accurate as far as the graph goes, but this underneath here, I'll use black. This is going to be L of x, okay? That's the linearization, the estimation of this value right here, which is going to be x equals 3.91, okay? So how do we find that? Well, we talked about this tangent line, and what we do for a tangent line is we take the y value that we're given, so that's f of x. We add to that the slope of the tangent line, that's f prime of x, evaluated at, well, in this case it's going to be 4, but let's just put x for now. Okay, and then we're going to multiply this by, so that's rise over run, we're going to multiply it by the difference between 4 and our estimated value. Okay, so it's going to be x minus x1. Now this is going to be, this f of x is really going to be kind of like y1. Okay. Okay, and that's the point, in this case 4, 2. So that's going to be x1, y1. So it would be x1 and y1. Now this right here, this x in question is going to be this 3.91, guys. So that's what we're going to do. We're going to do this. The approximation is actually going to be, what's the y value of the given point here? That's 2. What's the slope evaluated at 3.91? Don't know yet. We're going to find that out. Okay? Or, yeah, 3.91. No. That is going to be slope evaluated at 4, correct? 4, that's right. This is going to be x and x1 here, so again, this is going to be the difference between 3.91 and the x1 value, which is 4. Okay. And technically, in your book, you'll see this as, I think, f of a and f prime of a. And that's going to be this point that is known, that we begin with. So this is going to give us this value here, L of x. It's going to give us the y value here for this. And again, this is your, okay, this is what we just worked through. And this right here is sort of the formula for that, right? So I'm going to put that up at the top here. Okay? That's the linearization formula here. Okay? All right, so if we do this now, you guys have probably jumped ahead and done this, right? So we've got 2, this slope here, we worked that out earlier, right? The slope, the function is root x, and so the derivative is 1/2 x to the negative 1/2. So that is 1/2 of x is 4 to the negative 1/2. And that is 1 over 2 times root 4 over, or 1 over 4. So this right here, for the graph y equals root x, which is this red graph right here, we have this as a value for the derivative. 1/4, oops, 4. And this is going to be what? Negative 0.09? And does that look right? All right, so this should give us the approximation that we're looking for on our graph. So what's that going to be? 2 plus, what's that going to be? Negative 0.0 what? 0.0225, and so this is going to be 1 point what? 1.9775. So that means that we have used calculus now to find out what the square root of 3.91 is. Because this L of x is going to give us the point on the blue graph, which is going to be very, very, very close to the point on the red graph, or y equals root x. So now when we're done, we can just confirm this. So the square root 3.91 is 1.9773. So we are very, very close. That's a good approximation. Got it? Okay. All right, so that's that example there using local linearization.